All right. So let's learn about how we calculate the spring force, or the force in a spring. So this one's pretty straightforward. You can find this one pretty easy. Uh, if you have not yet done the Hooke's Law Lab 5.2a, stop, do the lab first. You don't know what we're talking about. One group, you've already done it. The other group, you should be doing it first. Go on to the Lab 5.2a in Classroom. It looks like this. Bring you through this FET applet, and the actual setup looks like this. It's a quick run through of more or less what we would do physically in class. And don't worry, this sort of setup that we do in class is not terribly thrilling anyway. So we have some big ones. They're kind of cool to play with the springs, but we'll see whether we can pull that off this year. So stop, do the lab first. All right. Anyway, let's get back over here. Assuming you've already done the lab, how do we directly calculate the force in a spring? All right, so force in a spring, real simple. You got a spring, it has to be attached to something. Here it is. It's got some sort of end, and you pull on it. There it is. There's your force on the spring. That's it. Now the spring, of course, resists. You pull, spring pulls back. And in fact, what you'll find is the more you pull, the more the spring pulls back. Now, in the process of your pulling, the spring will stretch. So at first it's this length. And then when you pull a bit, it will stretch out to something like perhaps this length. And then when you pull some more, it'll stretch farther rather, to perhaps this length. And the relationship you find actually looks exactly like what you found in the lab. You found you did a force versus displacement, technically is what we wrote, but you did a number of different displacements and a number of different forces. And you found that as you increase the force, you increase the displacement, and the data looks something like this. You got this linear relationship. There it is. And so this actually was a y equals mx plus b. You plotted it. Y, x. You found the slope of this. And your y equals mx plus b, which went through the origin, had a y-intercept of 0 in the case of the lab, was actually this equation right here that's on your reference table, page 6. Here was your y. Here was your m. Here was your x. And b was plus 0. In the case of the lab, y equals mx plus b. So the force on the spring was the y. That change in spring length, the x, was the x, conveniently, and the slope was k, the spring constant. So this is a force. A force is a force is a force, which means it's a vector. You draw it with an arrow like we've been doing. The unit is Newton, which is in fundamental SI, the kilogram meter per second squared, and you measure forces with a scale. In fact, one of the sort of scales that we commonly use is called a spring scale. That's probably the scale you use for pretty much anything. It's got a little strip on the front with a scale along the side. This is now a numeric scale, numbers along the side, a little hook on the bottom, and you hang things from it. And when you hang something from it, it actually stretches downward, and the little marker moves down to a lower spot. And you say, oh, well, look, there's the force now at this location. This is a spring scale. What's inside of this is a spring. You've seen these at the supermarket. A lot of them now you see are digital, so you don't notice it. They have a pan on top and a unit down here. But when you sit something on it, like your, let's see here, your oranges, here, your red oranges, this scale actually compresses a bit. There's a spring in there. The more obvious kind that you've seen that's most certainly spring is the big face dial scale. It has the 3 chains hanging here, has a big pan underneath, and you can put your oranges in there too. Those red oranges. And the dial, which normally reads 0, moves over to somewhere over here. Maybe it reads a pound, whatever it is. Okay? So these are all spring scales. Your bathroom scale at home is a spring scale. Okay. Those digital balances you used in chem, those are scales too. So they have a spring that compresses essentially, and from that, you can figure out how much weight is pushing on it. Now, we'll talk about why that maybe works here, and if you brought it somewhere else like the moon, why that might be a little funky, but we'll worry about that later. For right now, simple. Fs equals kx, that's really all you need to do. So what can we do? We can mess with the equation a little bit. Just understand spring constant. Now, this is an important concept. You really don't get into the meat of it until AP. I might give you a little bonus lab on it through the FET. And where is it? Over here. Not this one, but one of the others. And get you thinking about a little more where this spring constant comes from. What you should understand, though, is the nature of the spring determines its constant. It's just the stiffness. So if you ever look, if you have a garage door, you will see some very tightly coiled, heavy, thick springs. Those have a big spring constant. They help you lift a garage door. If you play with a slinky is very thin, very weak, it very easily stretches out. That has a very small spring constant. Okay? Your skin, by the way, has a spring constant. Pull your skin away from the back of your hand, let it go. It springs back to shape. Anything that springs back to shape has a spring constant. Your skin has a pretty big spring constant. Old people have small spring constants in their skin. How do you know? Lift their skin up and let it go, and it takes its sweet time relaxing back to smooth. That smooth we're talking about there is actually called equilibrium position. So the definition in your reference table for X rather is exactly this: the change in spring length from equilibrium position. Equilibrium position is like here. That's the unstretched position. That's like our zero. That's why when we did our lab, that when you started out with no pull, we said, well, it hasn't stretched yet. So that displacement, it's not that it's a displacement from your friend's house or from the end of the table. It was a displacement from its equilibrium position, from how it started. Okay, let's look at the units for these. Spring constant, actually look at this one first. Force is newtons. We've been doing that. Change in spring length. It's a length. Lengths always come in meters. Beware, though, that when we do problems, like lab problems, they'll often write it in centimeters. You may have to convert that to meters, so be careful. With those two, it's very easy to figure out a unit that you will probably not memorize. That unit is the unit for spring constant. So if you rearrange the Fs equation, your spring constant equals the force on the spring over that change in spring length from equilibrium. By the way, of course, that is the slope calculation you did in the lab. Rise over run, F over D, or Fs over X. So the unit for force is Newton. The unit for change in spring length, or any length in this course, is meter. So the unit for spring constant is Newton per meter. In fundamental SI, that's actually kilogram per second squared. I give you a little miniature extra credit. Show how Newton per meter is kilogram per second squared. With a little baby extra credit. Okay, let's get down here. Solving this is a piece of cake. A spring constant of 1,000 newtons per meter. Now, the truth is in the units. When you see a unit, Newton per meter, that is spring constant. I mean, it says spring constant also. But you come over here with your givens, units. K is 1,000 newtons per meter. Okay, fine. It is stretched over here. 0.15 meters from its equilibrium position. That's how much it was stretched. That's the X. X equals 15 centimeters, 0.15 meters. Okay. What force was applied to the spring? And it's implied here the force. What force caused this stretch? So what force? Fs equals question mark newtons. I mean, this is pretty light work right here. So there's your givens with units, your unsubstituted equation, your equation Fs equals Kx. And then, of course, substitute and solve. And you will substitute in there Fs equals, well, you know how to do it. 0.15 times 1,000. Yes, do this calculation. It'll take you less than a minute. 0.15 times 1,000 will give you 150 newtons. So do it. Okay. Now, let me give you one that's a little harder. A little harder, not a rough problem, but a little harder. Sometimes we don't make it so simple on you where we tell you K, X, find F. In fact, you may often get one that looks like this. There's a note here. Recognize that the force on a spring, a very common situation, is this. The force on a spring is a weight or a mass either hanging from it or sitting atop it. And so that will commonly be the scenario, and that's one way we can catch you sleeping. So the force on a spring often comes from a hanging weight or mass or a sitting weight or mass on top of the device. So let's check this one out. A 3-kilogram watermelon is hung from a spring scale at the supermarket. So I'm gonna make a little sketch of this. Here's your little spring scale at the supermarket. There's a little chains over here. There's a little pan that it's in, a little bucket, whatever it is. And we got our watermelon. Why is watermelon so expensive? Go to the supermarket, buy little chunks of what? Like 4 chunks of watermelon. They're like $8 for it. Anyway, it's a little watermelon. Now we know a few things about this watermelon. We know it's mass. Don't mess around. Mass is not weight. It says kilograms. That's mass. Mass is 3 kilograms. Okay. Good. Now, it's hung from this spring scale. So what we know here, are there any forces acting on this? Yes. Yes. Mass is not a force, however. Actually, the watermelon is being pulled down. The thing that's pulling it is the force due to gravity. Now, is there something balancing this force due to gravity? Yes. Yes, there is. However, it is not the normal force. Well, technically, there is a normal force in here. There's a normal force from the bottom of the pan. And then there's a tension force on the chain in here. But we're going to skip all those intermediate forces for right now because we're not quite to unit 6. We're going to jump to, is there a force from the spring? Let's take a wide view, an outside view from this. Is there a force from this spring inside of this little scale here, pulling up to balance out the weight? Yes. Yes, there is. We call that force in the spring, Fs. So these two balance each other. When you put the watermelon in, sure, it might bounce around for a moment, but it settles down. And once it's settled down, it's important for you to recognize that really there should be absolute value over here. The directions are different. But you should recognize, in this course, we don't really stress you on that this force from the spring here has to balance out the weight from the watermelon. Now, of course, it's more complicated than that. The ground or the pan is actually pushing up to balance out. The watermelon is being pulled down. It's pushing on the bottom of the pan. The pan is pushing up. That's a normal force. The pan is pulling down on the chain. The chain is pulling back. That's a tension. The chain is pulling down on the spring, and the spring is pulling back. There's your spring force. But all those intermediate steps, essentially, this is going to be equal. The Fg and the Fs are going to be the same as each other. So let's keep going with our givens for the moment. The spring stretches 2.5 centimeters. Well, stretch we know by now is x, and that's 2.5 centimeters. This is about as hard as our spring problems will get, by the way. And finally, the question here is determine the spring constant. K equals question mark. Now, you could have gone and written a whole bunch of things over here like, oh, Fg and this, but remember my recommendation for problem solving. Go in order. Write the givens first. Technically, I'm going to do this in Newton per meter, by the way. You could do this in Newton per centimeter. Let me come right down here. Newton per centimeter, notice this is an open-ended question. Newton per centimeter is legal. It is legal. In fact, I may show you both real quick. But notice the protocol here. It's the best way to solve a problem. Write only what is given. Don't do any math yet. Don't do any adjustments. Just write what's given. Now, we need an equation that will solve for the question mark given. That equation must involve the letter K because that's what we're looking for. The only equation that we have at our disposal with K is this one. So I'm going to rearrange this equation down here. Rearrange to solve for k. K equals Fs over x. Okay. So if we look at this, we already know x. X is good to go. In fact, we may just want to convert this to meters, which would be centi, just means 10 to the minus 2. So you could write 2.5 times 10 to the minus 2 meters. That's fine. Good. Or you could write 0.025 centimeters. That's fine too. All right, do we know Fs? Oh, Fs a little trickier. We've got to figure out Fs. How are we going to get Fs? Well, you're going to pump your feet. That's all. That goes back to this picture and the note up here, the realization. The short version of this fancy picture is that the force from the spring is going to have to match the weight of the object. So if you recognize here that the force is going to match the weight, and you're like, oh, well, how do I get the weight? Well, you know how to get the weight. We've been practicing this. The weight is actually, since we are spring scale, watermelon, supermarket, near Earth, the weight is just mg. And so you put your 3 kilograms here times your 9.81. Be a little more careful here. Like you could approximate 30, but I'm going to be a little more careful here. 3 times 9.81 gives you about 29.4. It's okay to go one extra sig big in the middle of your calculations, 29.4 newtons. That's the FG. And then the FG is the Fs. That's an S there. Sorry, you don't notice that. That's an S, which means we know the Fs now. Boom. And so to solve this one, K equals, you have your 29.4 newtons over your 0.025 meters, and you should get exactly this, 1,200 newtons per meter. If you did this in newtons per centimeter, totally legal, you would have had a 2.5 under here, and this would have come out to 12 newtons per centimeter. And that's legal. And that makes sense, by the way. If it takes 1,200 newtons to stretch this thing a meter, it only takes 12 newtons to stretch it 1/100th of a meter or a centimeter. Okay? And so now you're going to do W512, which is 4 questions, one side of one sheet. It's pretty straightforward. Here's a spring. They tell you the length, and then it's stretched to this. Remember, X is how much it's stretched. X is how much it's stretched. Same thing on number 2. X is how much it's stretched. And notice here I gave it to you in centimeters. Number 3, just like the scale we were talking about before, this is a sitting on top scale. I gave you the mass, so beware. You can turn that to a weight. And then finally, we did one on the moon. All right? One on the moon. And that one on the moon is a hang problem. Be careful, because when you use this sort of math that we just did, the weight on the Earth is 9.81. But the weight on the moon is going to be something different, because the gravitational field strength is different on the moon. All right. That's about 17, 18 minutes, something like that. Perfect. Take up the whole class. Learn it.